Hello, God bless you, and thank you for watching my videos. Please like and subscribe to my channel, and if so moved, contribute to sponsor my research and ongoing scholarship via the PayPal link and or whatever other means I may provide in the future. In this video, we're going to pick up where we left off in part 4 and jump right into multinomials and then show how ultimately they are intimately connected to partitions. And I continue my rant on conventional notation for binomial coefficients. But please don't clutch your pearls. It's meant to be an exploration of an alternative way to look at this stuff in a broader context to hopefully save you from some of the frustrations that I've experienced. I will calm down and nail Vandermon's convolution in part 6, I promise. In part 4, we talked about binomial coefficients and started to get into multinomial coefficients, and with the suggestion that just looking at multinomials and focusing on multinomial coefficients as a whole might actually be simpler than looking at binomials, because we just start with this one definition of x factorial under some partition of x. I should say x factorial divided by the product of the factorials of the elements of a particular partition of x, so that there would then be p of n where p or n, the partitions function, would count the number of multinomials associated with x on the top or n on the top, as the case may be. And with this definition, it's like, boom, we're off to the races. And so here, for example, we started here in the bottom with the quadrinomial, and then the trinomial, and here's our binomial. And if we go up further, we get our monomial. But notice the notation for the binomial has the a and the b underneath. How hard was that? No, let's just force anybody who looks at the symbol ever to have to do the subtraction of the lower from the upper to see the other side, which is actually nothing but an alternate notation that we also invented. Starting from the get-go, looking at multinomials as a whole from this view, it jumps out that the lower numbers are just a given partition of x. The number of partitions of x is just the number of ways of writing it as a unique sum of numbers less than or equal to itself. See my videos on quadratic polynomial number theorem on my channel for a lot more information and thorough explanation of partitions. But the gist of it is, take for example the number 7, the number of partitions, and this is corresponding to the far right column on the screen. The number of partitions of 5, take p of 5, is 7. There are 7 ways to have a unique set of numbers less than or equal to 5 that sum to 5. So if the upper argument of your multinomial coefficient is 5, there are only 7 multinomials that you can have if your lower arguments are going to be split into integers, positive integers. So here on the screen, let's list out the 5 partitions of x equals 4. And then let's look at the 5 resultant multinomials that are possible when x equals 4. We can call these the multinomials of 4. And you don't need a new counting function. You already have one. It's called a partitions function. And the column of values you get in descending order according to ordering partitions gives you these stacks of numbers that are intimately related to the factors and divisors of x factorial, 24 in this case. So if our research is is guided by seeking to unify and define and explore these broader connections on more general bases. The binomial coefficients are going to take care of themselves. They're going to come along for the ride. All of which is only worth mentioning because if it's such that we are in some area ultimately trying to construct these broader connections, because we can kind of sort of see them and we're exploring the broader connections, but with only the binomials or relying on binomials as the as building blocks, you just might be making things way more complicated than you need to. Let's look at another example here. For x equals 5, there are going to be 7 partitions of 5, and thus 7 multinomials of 5 in integers. Similar to binomials alone, if x is a prime, then all of the multinomials of x, here 7 of them, except for the number 1, the first one, are going to be divisible by that prime. And these columns of multinomials are very much the same kind of sort of, the same structure that we have when we're looking at divisors of a number. And so the possibilities for integrating the two together are just really underexplored, I think. I do another example for 7 here. The number of partitions of 7 is 15, and I thought I was writing them out here, but I actually only wrote out 14. I missed 3, 2, 2. So I will list out the multinomials for the ones that I do have there, just missing that one. And then I do a bunch of stuff which is just not even relevant now because of that mistake. I don't even want to even try to talk through it. But we'll show you a couple things here, and the first of which is here. Notice that the column of descending multinomial values is not strictly increasing. So it goes up, and then drops back down again. So I'm going to show you where that comes from. They're basically grouped by the leading element in each partition of X. But notice that the subcolumns also appear to be strictly increasing over their short ranges right here. But everything to the right of that first element in a partition grouped that way is just a partition of the number 1 less than itself. See right here? Look to the right of 3, to the right of 4, and the numbers on the other side are 3, 2, 1, and 1, 1, 1, the 3 partitions of 3. So as x increases, the subcolumns will always end up with this property of never being fully, always strictly increasing, even within their own grouping. So if you wanted a simpler notation for a binomial coefficient with less information, why not something like m and then the 2 numbers on the bottom? That way, to figure the number on the top, you just need to add them up. You know what I mean? Instead of subtracting. And you can think of it in terms of like a seven buckets for 7 factorial, or 7 balls and buckets kind of a thing. Where you carry the zeros, because 0 factorial is 1. So these are all would be perfectly valid expressions of a multinomial. Where if you wanted to add the top argument by adding together the numbers on the row, you could put that in a preface, and that's not too bad, a little comma, and followed by the partition of that number. And this is, of course, the pervasive structure of partitions themselves. This little diagram here, I'm not going to spend too much time on it. You can freeze if you want and look, but the interesting thing about it is that every partition is going to have, if you discount the first element of every partition, the what remains in the other elements are these partitions, full-blown partitions of lower numbers up to the floor of the of n over 2, and then with the top getting cut off as you go higher up. And it's a pretty fascinating structure, and it just carries right on through to multinomials. And the one thing you can always guarantee is that that span of that column is going to go from x to x factorial, and everything in between is shares divisors. In the next video, we're going to see how van der Mon's identity plays on Pascal's triangle, but not this version on the left, but the Cartesian version we've seen. The triangle on the right represents another key relationship to the binomial coefficients of Pascal's triangle, and that's covered in quadratic polynomial number theorem discussed. But that's the last we'll talk about partitions for the time being. And in part 6, we're going to focus down on what van der Mon's identity looks like on this thing, or the Cartesian version of this thing. Thank you, and God bless you. In the meantime, please like my videos, subscribe to my channel, click the bell notifications icon to be notified when new videos are uploaded, and please click on the PayPal link to make a donation to support my further research and scholarship. And anybody who makes a donation before part 6 comes out, put an email in the comments on the PayPal donation form, and I will send you a link where you can watch part 6 in advance, maybe more by that time. Thank you, and God bless you.